Okay, folks, hi. So here we are for week 2. I'm going to apologize in advance. This lecture might seem a little bit chopped up a bit. I'm going to have to steal it in between moments with the kids. As you know, there was the snowstorm on Monday. Yesterday, I did send the kids to school and daycare. I can already hear them starting. Let them give me like a few minutes and I'll come in. We did send them yesterday. The school bus isn't running. Access to school is impossible. It took like hours to get to school to even drop them off at school. And then I know that at daycare, a friend that they didn't overlap with, but I know the whole family is tested positive for COVID. So I know it's just a matter of time. They had been at daycare last week, even though my kids weren't. So out of an abundance of caution, I've pulled my kids from school and daycare this week. We have no care. We're both absolutely jammed with work and teaching and all the stuff. Plus now I'm helping out the friend that their family did test positive because they weren't prepared for it. So I'm going to be running a lot of errands and making meals and dropping them off and stuff, because that's exactly what you do in a small town, and you help each other out. You should be doing it in a big town too. You help out your neighbors. So I'm going to be sneaking this in between the breaks when my kids are breathing and we're all calm here, in between the yelling, if you will. So it's a good lecture for this. It's a nice light lecture. I'm trying to ease you guys in. I know it's bonkers for you guys too. That was my sob story. I know so many of you are going through difficult things and how hard it is for everyone. So I get it. I understand. This week's lecture, some of it is some time you're going to take on your own to just look at some things. And I know you're going to think, well, what do we do while we look at these things? Read them, see if you understand what they are. If you want, make a list of questions for what you didn't understand. Happy to answer them next week, where the TAs could jump in and help you out on it. And if they can't answer it, then you guys can come to me. So this week we're going to talk about structural drawings, kind of some key things that you see on structural drawings, what they look like. We're going to talk about tributary area, because we're going to need to just understand tributary area and tributary width as we go into later on in the term. I'm going to give a brief intro into the project, and that's it. It's a relatively short lecture. So let's get into it before a child comes running in. Hopefully clothed? Are they clothed?
Yeah,
they're not clothed. Okay.
No, they're happy again, so I'm leaving them.
Okay, so structural drawings. It is kind of expected that you already know how to read them, which is crazy because when have you had the opportunity to read structural drawings? You probably have a lot of experience at this point with architectural drawings, or maybe not. Maybe next year is your first opportunity when you do comprehensive. That's not exactly clear to me, but there is an expectation that you're being exposed to them and you're figuring it out. So what I have done is I have provided for you on Quercus quite a few things. One is a series of projects that I have worked on where I've provided the architectural and the structural drawings for you. I'm going to flip ahead and see if I mention that. Yeah, okay, so that is on there. So let's just talk about a few quick things. One of the things I've provided on there is a thing called typical details. Those are the things that are so common and so basic, we assume that the contractor already knows it, but if we don't put it on the drawings, what a pain in the butt. So we put it on the drawings, and it's kind of like a capture all. These are the things that are so basic, anyone involved in the project should know this. But I'm going to admit, a lot of the times people don't. But they're so ubiquitous that we don't want to have to redraft them every single time. So most companies, most firms, and architects have the same thing, a set of typical details. And they usually populate the first few pages of a project. And if it's a small project, maybe you have 5 typical details. If it's a big project, maybe you have 30 typical details. You would still go through and cut sections to try to show what's happening. But these ones are the ones that will capture all the loose, small stuff that you shouldn't need to draw every single time. In the drawings, though, there's a lot of acronyms or shortenings of words. This is one of the sheets from the typical details, and it's kind of expected that you understand these. You're going to see me use a lot of these throughout the term. C/C means center on center. So that means from the center of one thing to the center of its similar thing, that's the distance. So for example, wood joists, we often say, are 16 inches center to center, or on center, O/C. And we're saying that 16 inches on center is how often that thing occurs. CANT is an abbreviation for cantilever. We looked at what cantilevers were last week just a little bit. That's that little bit that overhangs the edge. CA means column above. So depending on how we cut drawings, because we're cutting a drawing, we're trying to take a representation of a 3D thing and represent it in 2D. Are we cutting above and looking down? Or are we cutting and looking up at the ceiling? And there are different ways to do that. And I'm going to talk about that in a few minutes. But CA usually means column above. So if we have a beam that's supporting a column above, we wouldn't be looking at it if we're cutting below. And we're gonna look at that in a few minutes, so don't worry about that too much. But we would often put CA to let us know that that's not a column supporting the beam, but it is a column adding a big load to our beam. GA typically means gauge. I'm going to see if that's exactly what we have here. Yeah, so GA, gauge. Now, you have these typical details, and this is listed in that. Gauge is, if we're talking about really thin pieces of metal, they'll often talk about it in gauge. And we're really talking about how thick it is. Often, engineers in Canada will convert that to metric, where we'll actually say how thick that thing is. But metal deck, for example, which we think of as like you couldn't bend it easily with your hands, you would need tools to try to bend it, is less than 1 millimeter thick, typical steel deck. So we have it in our heads that gauge level material is like the thickness of tin foil, but it's really thick, substantive stuff. Small k with a capital N is kilonewtons. We're going to be working in the units of kilonewtons a lot throughout this term. I showed you how to convert them last week, and we're going to talk about what a kilonewton is next week, I believe it is, in the term. MC, moment connected. Moment connected means that something is continuous. For example, our cantilever. If we have our cantilever over here, and this is our backspan, this is continuous across here. But what happens sometimes is we want that to be a cantilever, but we can't put it in like that. What we might do sometimes is cut it here and then put it back together, or we might cut two different things and put them together. When we put them together, we're saying it's acting like it's continuous. It is one solid thing at that joint, and we're saying it's moment connected there. MOM is another way of saying moment, so sometimes we'll refer to that as moment. Open web steel joists, OWSJ. That is something we use a lot in steel structures, not to be confused with wood joists. They're a very different thing. Open web steel joists, I have a slide of them in one of the next slides to show you, but you've all seen open web steel joists. In this context, we're talking about reactions or radians, but radius, but often reaction or radius. So you'll have to look at the context sometimes. SOG, slab on grade. That's the bottom level surface of your building that touches soil. Very rarely would we have a building without a slab on grade, but most buildings have a slab on grade and it is directly on the soil. And we'll talk about that this term. UN, U/N, unless noted. So remember I talked about wood joists, 16 inches center to center, unless noted. Because maybe there's a location where we have a big gap because there's a hatch that needs to go down there or something. But that would be unless noted, U/N. You might often see me write B/C, which stands for because. All right, in this term, these are the major ones we're going to talk about. CF, factored compressive force in kilonewtons. So remember I said if it has that little subscript F beside it, it means we've applied all the load factors to it. And remember if it has the subscript R, we're saying we've reduced the compressive capacity of that member. And remember, the reduced capacity needs to be greater than the factored load on it for whatever force type we're talking about, whether it's compression or moment or shear or tension or torsion. We're not really going to talk about torsion in this course, but it's nice to know that torsion exists. So these are the ones we're going to talk about this term. Next year in Structures 2, we're going to be talking about all the little subscript R's. So instead of CF, we'll be talking about CR. We're going to be talking about CF too. There's a kind of a continuity between the two terms, but we're going to focus on that compressive resistance next term because we'll already know how to calculate the factored compressive load. And so we'll be, instead of MF, we'll be focused on MR, VR, and TR. All right. We're going to take a few lectures this term and just talk about building materials. Now, I had understood when I started teaching this course. Are you sending us texts, buddy? Oh, that's a great picture, buddy.
It's a picture of Duncan.
That's a very cute picture of Duncan, buddy. Hey, I'm recording my lecture for a few minutes. Is that okay, buddy? I'll let me get through this slide. Sorry, I apologize, guys. This one's going to be really fractured. I don't quite know what else to do and how else to handle it. The assumption is that you guys know how basic buildings go together, and that you're jumping into it knowing that. And now all we're going to do is talk about crazy hard stuff. But the fact remains is you haven't seen how basic buildings go together. And there's not really a place in the course to do that. Since I teach structures, everyone really asked me if I would fit that into my course. When we only had 10 two-hour lectures each term, it was really tricky to add this in. But we've since extended the time slots so that there's 12 three-hour lectures in each course, which is that's a huge difference in lecture time. So I now have 2 lectures dedicated explicitly to building systems. Open web steel joists fall within that, and I talk about them extensively, and it's where we talk about the sizing guidelines as well. However, this one I think you guys need to have an idea of just before, because we write it in an acronym, and it's a funny one even in English, and I know a lot of you maybe English isn't your first language. So I wanted to show you an image of what an open web steel joists, or an OWSJ, is, because you've probably seen them, and it's just helpful to see it here. So it's basically a miniature truss. They are made by a fabricator, meaning they're a proprietary product. I would just specify the depth even on my drawings, and it would be designed by the owner, but I'd need an idea of which one. So the people that make these supply me with a chart, and I can pick out, based on the loads on it, which one is applicable, but they will do a final design with signed, stamped drawings. Okay, I'm going to fly through a few of these things. I'd just like to get to the next segment, and then I'll stop it, and I'll go spend the day with my kids, and the next time you see me, it'll be late and I might have a glass of wine, apologize in advance, but if it's 9 o'clock at night, I'm going to have a drink of wine. I'm assuming some of you are watching this in your pajamas. Maybe you're drinking a coffee, maybe you're enjoying some other substance, but I might have a glass of wine while I'm filming later. So these are hatches. Now, we use hatches to help us at a glance see what material we're looking at. A hatch is something we use when we cut through something. So if I'm cutting a section or I'm cutting a plan, if you see hatching, it means that we've cut through a solid object. So if this is my floor plan and it's held up on columns, and I am cutting right through here and looking up, I would not show the paper hatched, but I would show the column I cut through as hatched. So these are some of the earth materials. These come in handy when we're doing our foundation drawings. So rock, general earth, fill or bad material. If we're doing gravel that we're putting back in, it would be this. Fill for sand, but we'll often do this for a large scale concrete hatch as well. So some of our materials. Brick is a tight spacing hatching on the diagonal. Block is the same thing but a little bit wider spaced. Cast concrete, if it's a large scale like 100, we might actually do just the same grout or sand hatching, but we'll often show little triangles to show that it's sand and gravel. If it's a detail, we'll often show the reinforcing in the image as well. And if we're cutting a detail through a beam, you'd see even more hatching or more reinforcing. Now remember, you guys have these drawings, or you have some of this information in the typical details. Metals. I don't even know why I bother with this one. It doesn't matter what metal it is. I draw it all like steel, which is on the diagonal, 2 hatches, 2 lines tight together, and then a gap, and then 2 lines tight together. It says copper and aluminum would be different. No matter what the metal is, if it's a metal, I cut it like it's steel, and I've got a note saying what it is. Wood hatching. For a stud wall, we try to cut it with like this little curvy pattern to show that we're cutting through wood. This would be cutting through a wood beam. So if we've cut through a beam and we're looking at a wood beam, we'd do an X on it. If you've got 2 pieces side by side with separate X's, we're saying this, for example, maybe is a 2x6 and this is a 2x6, and we've screwed them together. And then this is plywood. It's several hatches, several diagonal lines tight together with a spacing. Some people draw 3, some people draw 4. Okay, I'm gonna stop here and pick back up a little bit later, but this was helpful. Thank you guys. Okay, my husband has said he'd take the first round this morning, meaning I get to do a little more of the lecture this morning. So some of it still might end up being tonight, so I've made another coffee and we're ready to jump into structural drawings. So I have created for you specifically a fake building. Now, I have created the building in steel and I have created the building in concrete. Malcolm, I'm recording a lecture, buddy. Could you go put clothes on and not come out here, buddy? So I've created 2 versions of the same building, a steel version and a concrete version, and then I've created structural drawings for it. Now within those structural drawings, I've done something specifically for you guys. I've put the notes that would normally go on the set of structural drawings, but then I've also in light gray added some notes that are specifically for you guys to try to help explain what's happening. They're things that wouldn't typically be written on the drawings. Now, some of the things that are helpful for you are the normal things that would be written on drawings. So we're gonna look at those. I've brought up the PDFs. I've put some bits of it in the lecture slide, but really I would recommend you open up those PDFs and take some time. I'm gonna show you some highlights, but the idea is that you're going to be taking a look at them. I have been adding to these each year since I made them. So at first it was just the plans, and then I created some schedules. Then I created some sections. And next year I'll probably add a bunch of details. There's a kid hurt now. And so next year I'll add some sections to it. The idea is that, I would get paid $50,000 to create a project like this over months of time. So I can only do it piecemeal for you guys. So I keep building on it each year. What I've also done, though, is communicated to some architects that I've worked with. And in the helpful drawings module, I have also added for you some projects that I worked on, that I have a set of the drawings in architectural and the structural drawings. One of the projects we actually did in steel and then in concrete. There was a really good reason for that, and I'll talk about that when we get to it. But in my fake project, the things that are helpful to look at and for you guys to be able to recognize that are very important in a set of structural drawings is grid identification, grid dimensions. If we set things on grids, that tells us how long things are. Remember, the whole idea of structural drawings is I should be able to hand them over to a contractor, and without ever speaking to them, they should be able to build the project I told them to build. They should be able to do exactly what I said. So all of the dimensions of everything need to be explicitly or derivable from the set of drawings. What the materials are, what the member sizes are, where in elevation they need to be, all of those things need to be in the drawing. Somebody needs to be able to build from it. Somebody needs to be able to price it, and we need to be able to tell the building department we did all the right smart things, but somebody also needs to be able to build it. And it's not me building it, so I need to be able to communicate with somebody how to build it. So grid identification and grid dimensions. Labeling. If you just draw a beam, nobody knows what that beam is. You need to either label it with what size or what member it actually is, or give it a name and somewhere else have a list of the names with what those members are. So that would be the sizing. Maybe your label is the size, or maybe you have a label and somewhere else off to the side you have all of your labels equated to a size. We need the framing. You actually have to be able to show how this goes together. Really, our drawings show that it's stable. Within our drawings, we should be able to show that everything's stable. We're going to talk about free body diagrams later this term, which is really a way of drawing something stable. And it's going to be helpful for us to do math with those. It's a starting point. But really, the basic concept of a free body diagram is showing that it's stable when we're talking about structures. The framing plan, the free body diagram is implicit in that, or we are showing a very simplified version of it. In that framing, we need to have a gravity system, and we need to have a lateral load resisting system. I found my little tools for showing you guys lateral load resisting systems, and where did it go already? Hold on one second here, team. I dug through everything and found it. Here it is. Okay. Lateral load resisting systems. This is a wall. It's got or it's not a wall. These are columns, and this is the beam at the top. That tips over. These are able to rotate here, so they're able to just tip over. That does not have a lateral load resisting system. If all of our building was a series of these along its length, the whole thing would still tip over. What we can do is put this in here. This is a brace. This makes it stable. That is our lateral load resisting system. Another way we can do it is, oh, my new phone isn't the same size. My calculator? Yeah, okay. So this doesn't quite fit. Doesn't fit at all. Used to have something that was the perfect size right here. My wallet? No. Well, anyway, a wall is when we fill this in perfectly. What I'll do is I'll cut a piece of cardboard for the next time we talk to each other. Switch game? Oh, no. Okay. So you could imagine if I cut a piece of cardboard out and fit it in here, it still wouldn't tip over. That would be a shear wall. Now we're gonna talk about all of these things later in the term, I promise. But this is your first identification of a lateral load resisting system. It's what stops it from tipping over. We also, in plan, so if this was our floor, we need it to not do this. This is called skewing. We need our floor to not skew. So in plan, we would often do something like this. Although, what do you often have sitting on something? A deck of some sort. Plywood, maybe you've got a concrete floor. There's something, you don't want people to fall through the holes here. In a wall, you want a doorway here. So this kind of makes sense. But for a floor, you don't want anything to be able to go through here. So we often, already embedded in this, we have something here that can act as our lateral load resisting system in our diaphragm instead of that. But again, we're going to talk about all of that later in the term. So don't worry about that right now, but I am going to identify the lateral load resisting systems in the drawings. And you guys will need to do the same when you get into structures too. It's going to be very important. Cantilevers. Cantilevers can be shown two ways. They can be shown as continuous over a support. So remember, this is our columns with a cantilevered beam, and this is one continuous member. I could cut this pen here and glue it back together, and that is also a cantilever. All right, so let's see what I have in the drawings. No, I just have the drawings like that. So I'm going to pull them up in PDF for you guys, just because it's a little bit easier. Okay, so this is our steel building. Let's see where we start with this. Not the first page. So here's the first page. You can see that I have a name for this plan. I've identified what's on this plan. I have a scale. Scale's really important. If you don't have a scale, you should show some dimensions because you need to be able to tell people how long things are. Remember, somebody needs to be able to build this. But a scale is helpful. I've got the normal stuff, like what my project is, who's done this work. I've said when I've issued it, so I created these drawings. So you can see I started this project in 2019, my fake project. I've started putting pieces on this every year. So this project in a way is tries to include all the things, which makes it a bit of a ridiculous building. I don't think anyone would actually build this building, but I've seen parts of this building in other buildings. So this is representative. I'm trying to grab all the things I could imagine you'd see in basic construction and put it in one building. But that means we have some things that would not be normal in a building, if you will. So let's take a look. Looks like this is the outline of our building. We've got grid lines. So I've got A, B, C, D, 1, 2, 3, 4. And I've got dimensions between all these grid lines. So grid line A to grid line B is 3 meters. Looks like I've got some section cuts here. So somewhere in this set, it looks like somebody took that building and sliced a line and This little arrow means that we're well, I guess for you guys, looking that way into the building. What else have we got here? Oh, look at this. Oh, that was weird. It says that this part is unexcavated. Now, foundations, so this, actually, let's see what drawing we're looking at here. We're looking at the foundation plan. So it's the basement floor datum is at 0. So the basement floor is at 0, and that's at geodetic elevation 205. Where crossed and noted the local datum for raised or lowered areas is given to the basement floor. There's some other notes here. Okay, so these are the normal notes you would see on a set of drawings. Look at this. Found footings on soil capable of supporting 150 or 100. All footings to be minus 1.22 meters min for frost protection. These are things we're going to talk about later in the term. 100%. In fact, this line here is one that I will definitely have in the final exam, promise. But we'll talk about it again, so you're going to hear me say that more than once. These notes are the ones that are explicit for us to talk about. So the light gray notes wouldn't normally show up in the drawings. They're the things that are already understood by most people looking at the drawings, but I thought you might not have seen them before, so I wrote them out explicitly. So foundation drawings are typically cut above the basement floor plan or footings and look down. So what we're saying is, if this is our building and this is the basement, ground is right here, level 2 is here, and the roof is here. So if this is ground with a ground floor and this is a basement, we're cutting in between those two things and we're looking down for our foundations. I'm going to tell you that's the only time I do that. It's the only time I cut and look down. So concrete element beyond another structure is shown dashed because we can't see it. And anything that we're cutting through is hatched. So let's take a look at what that means. So if we're cutting between the basement and the ground floor, we're cutting and looking down. That means any walls we're cutting through would be hatched, and the footings, which are below us, would be a solid line, unless it's below something else and then it's dashed. So this is our basement floor. So we're looking down at our basement floor. And it says it's a 150 slab on grade with mesh in it and saw cuts. This is our wall. So we're cutting through it, so it's shown hatched with solid lines. We're looking down at a footing. So here's a footing. This part of it is solid, but this part of it is dashed. What's preventing us from seeing this part of footing? Yeah, it's the slab. We've got the slab on grade here preventing us from seeing it because the footing is just underneath the slab. We've got dimensions here. You can see we've got more footings. Over here, look, these footings are drawn solid, and this says unexcavated. What this is saying is there's a basement here, but not a basement here. There's a ground floor, and so these foundation walls are just for frost protection to protect this part of the basement. We've got a note here. This is saying the bottom of the footing. So this says where the bottom of footing is in a geodetic elevation. This SDF means step down footing. If this is a basement, we have to dig down some amount and take out all that soil. This here, we have to dig a little bit where we're putting the foundation walls. And you saw a note on the drawing that said we have to be down at least 4 feet or 1.22 meters for frost protection. But 4 feet isn't enough for a basement, which means obviously these footings need to be a lot deeper. So we have to get from 4 feet down to someplace deeper. Well, you can't just go along with a footing and drop down and keep going. Remember last week I talked about how if you dig a hole in the sand and you stand beside it, it wants to push that soil in. Well, that's called an overburden. If we did that right here, we'd be pushing hard on these footings, and we'd be undermining this part of the footing. So what we do is we step it down slowly. And so these little arrows are telling us that from this datum to this datum for underside of footing, we're going to be doing some transition. And I show you that in the next slide or in the next page, so don't worry about it. We've got some stuff happening over here. Okay, we've got an elevator pit here. We've got a stairwell. So we're showing this stair. There, it looks like there's a doorway that you come in here. And you go up like this. We've got a little thing here that says sump pump. So usually we have to pump water out if ever it flooded in here. And so this is where all the water would drain to. What other pale notes do I have? Okay, so these are the things I told you about the slab on grade hiding this. So this is inside the insulating building, so it can be almost to the underside of the slab. This doesn't have to go down 4 feet because the building is protecting it from frost. This zone is unexcavated because there is no basement, likely at least partially excavated and then backfilled to support the slab on grade above. That'll be shown on the ground floor. So let's go to the next drawing. We'll come to this in a minute. All right, we've got all of the same grid lines. This says it's, whoa, that's weird that it's zooming in hard on me there. Ground floor framing plan with our scale. We've got section marks. So now look at this one. This has a basement underneath it. This doesn't. This part of the floor is sitting directly on soil. So we have a 150 slab on grade. It's the same slab as what we had in the other basement. We've called this one GS01 or ground slab 01. Let's see what we called the other one. BS01, basement slab 01. I called them 2 different names even though they're the same thing. I could have kept them the same, but in my experience, sometimes what might happen is I'd see this and I'd make a change here, but I didn't mean for it to make a change to this one. So I often would like to name them with different things. Sometimes the other way is helpful. It really depends on the project and what your intent is. Okay, so let's take a look at our notes here. Ground floor datum. Oh, look at this. Live load. Typical ground floor dead loads. We're going to talk about loads in a few weeks. All right, over here in our pale notes. This is cut looking up. So we're cutting through the foundation walls and in the right. So this is just before our ground floor. We're cutting looking upwards now. So we're basically cutting in almost the same spot we were last time. We're cutting in the exact same spot as before, but looking up now. So remember, basement, ground floor, second floor, roof. Before were cutting here and looking down. Well, now we're cutting in the same spot and looking up. So we're looking up at the underside of the ground floor, but we're cutting through all the basement walls. So we show our walls the same. We're not looking at the footings anymore. The footings were on the other page when we cut and looked down. So we're cutting here and looking up, which means we see the framing for the ground floor, and we see our slab on grade here, but we're cutting through these foundation walls. Now look, I've made a note CA, or column above. That's telling me that my column is sitting above what we're cutting through. It's helpful to show this column though, because it gives a little bit of context. It tells us that we've got a big point load here. It's very handy to get in the habit of showing your column above where it stops, even if it isn't on your plan. If this was 3 stories up, I wouldn't do that because it doesn't really have an impact on this particular plan. But I know at the top of this concrete wall, I have a column sitting here. And that's handy to let me know why I might have this notch out here. See, if I had brought this wall right around like this, there would have been nothing to support this column. So I kind of notch out my concrete here so there's something to hold my column up. All right. What other information? Oh, look, I had to add this dimension here because this wasn't on a grid line. Now, I would always recommend to an architect that we make this a grid line. If there is major structure on it, it is very helpful to give it a grid line name. Grid lines are helpful for architects, but they're vital for engineers. We really like everything to be on a grid line or major elements on grid lines. What I would often do, even if the architect doesn't have a grid line, is I would maybe call this 3' or 3x or a little I, something that I could then communicate in a schedule what line this is. Okay, what else do we have here? Oh, so before we had been cutting through a wall looking down, now we're cutting looking up. We've got our doorway cut, and look, you can see that we're showing framing for this stair. That looks, those dark black lines, that is saying we've got steel there. It looks like at our ground floor we had a cast in place concrete, but up above that it looks like we're switching to steel framing. There's our elevator. Okay, let's take a look here. GSO2. Well, our slab on grade was GSO1. This is our ground floor slab number 2. It's saying it's 64 concrete on 38 metal deck. Again, we're going to talk about that later, but just to help you out, metal deck, when I say it's spanning in this direction, so it's spanning in this direction, if I take this piece of paper and try to support it here and here, you know that it does this. It doesn't have any strength. But you know, and if you want to, try this out. If I accordion folded this piece of paper, so I'm just folding it like an accordion. I should have folded it in bigger folds. What do you think is going to happen when we accordion fold it? You instinctively know, and you instinctively know the best way to lay the accordion folded paper out. And this is where I always say, everything you need to know about structures, you already know. As soon as I make you write it down, it's like it just disappears from people's heads. It's kind of crazy. Okay, so I've got my accordion folded piece of paper like this. When it was a flat piece of paper, I couldn't make it sit on my hands. But look at this. It's the same dimension and it's the same piece of paper. And I've put it like this, supported in the same way, and now it spans from this hand to this hand. That is the span length of our element here. So, what happens though if I try to put it this way? You know, it still doesn't work. Intuitively, you know that. So when I show these arrows here on this deck, I am saying my deck is spanning like that. I am not spanning it in the other direction. It is not spanning in this direction. It is spanning across the top of all of these beams. So we have a series of beams here supporting this deck like this. So in fact, imagine this folded paper kept going and it was this long. It couldn't span that whole distance, so what I've done is I've put a beam here and a beam here and a beam here and a beam here and a beam here. The span length is the distance between those beams. If this paper was really, 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 really long, it still couldn't span that distance. It needs a support every so often, even though I've made it folded so it has some rigidity. So those flutes are running in this direction, and these beams and this wall are supporting the deck. You're going to get used to this. That means this cut here, I should be able to see my little flutes when we get to that. So let's just keep that in our head, 3SO2. We'll see if 3SO2 shows the flutes cut on that. All right, let's look down here. Let's see what this is. This says steel column schedule notes. So this looks like all the information about our columns. Look at this. Let's pick a column. Let's go to this one, A2. So A2, looks like here we've got a footing and a blob of concrete when we were cutting looking down. When we were cutting looking up, it said there was a column above, and we see there's a blob of concrete, and we know up above there should be a column above. We haven't looked at it yet, but let's see what A2 has to tell us. Very first one is A2. So look at this. Here's level 2. Here's our ground floor. It looks like our column starts just below the ground floor, and here's our basement floor. We were cutting here and looking down the first time. The second time we were cutting here and looking up. We have our loads, and we have something that says refer to plan for our footing. Let's go back and look at our plan and see what it said. Oh, look, 500 by 500 pier with 8 15s vertical and 10 at 300 ties, and a 2 meter by 2 meter by 300 millimeter footing with 820 bottom each way, dowels to match, tip and less noted at steel columns above. You don't know what the heck that was all about, but you're slowly going to start to learn. This 500 by 500, that's the dimension of that concrete holding up the column. This is just the steel that's in the concrete. The 2 meter by 2 meter footing, that's what's holding up that pier. The 20 bottoms each way, that's the reinforcing. Don't worry about that right now. Dowels to match just means that there's pieces of steel that go from this into this. Okay, let's go to the next page. Okay, level 2 framing plan. Things start to get a bit busier here. There's a lot going on now. Let's start with our notes. I find that the easiest. All right, level 2 framing plan. Level 2 framing datum. We've got some notes here. It tells us some information about loads. Snow load. It says ASL is shown. Well, that's accumulated snow loads. We've got low roof dead loads, balcony dead loads, interior dead loads. So there's all kinds of different loads. It seems like they apply in different spots. Like this looks like it's a balcony. This looks like it's a low roof. And this is the interior of the building. Let's look at our notes for us. This is cut looking up. So we are cutting between the ground floor and the second floor and cutting up, which means the columns from the first floor to the second floor are what we're cutting through. Anything above that, if it's not continuous down through the building, would be a column above. Let's take a look here now. Let's see what some of our notes are. Column above between second and roof impacts beam, so it's helpful to see even though we aren't cutting through it. So this column, now this is what's important. See this beam, 2B13? It starts at this column. See that it doesn't break here? It's a solid line that keeps going through. And then it's broken here. There's a space between this beam and this column. That tells me that this beam, 2B13, starts at this column and goes to this column. And this column here, CA, is a column above. So I have a beam supported here and here, and right here, there's a big point load coming down on it. This column above is sitting on it. Maybe we'll see that in this section. We've got, it looks like 2J01. Look at this. These lines are shown funny. They've got this double dash on them. Let's look at this schedule here. This is our steel beam schedule. Okay. Do we have 2J01 on here, or did we choose to put our joists notes right on here? Oh, look at this. 2J01, 600 deep tip. And then all the rest of these are labeled 2J01. So we're saying that these joists are 600 millimeters deep. It looks like we could see how often they exist if we knew what this dimension was and divided it by this many spacings. So we should be able to see how often these occur. We've got concrete on metal deck spanning from here to here, but it's got a support. It's being supported every so often. So this deck we wouldn't say it's spanning all the way from here to here. We'd say it's spanning from joist to joist. It's being picked up at those joists. We've got a stairwell here. This isn't concrete. This is dashed as block. Remember that wider dash line? 200 masonry block lateral load resisting system, LLRS, along grid line D and 4, 190 block remaining core walls with 15s at 400 grouted solid. Refer to typical details for the lintels. Interesting. So lintels are what's over the doorways. Stair and landing designed by the supplier. But look at this. We're showing that as a beam. What the heck is this big black chunk of stuff in the middle? Well, it looks like a big solid diamond. Well, one of the things we're going to talk about later in the term is that a black triangle or a solid triangle means a moment connection. So this is saying this is a landing, and this piece of steel is going to come along, it's going to crank, it's going to be underneath the stair, and then it's going to go flat again. But steel doesn't exist that looks like that. So what we have to do is take different pieces of steel and weld them together. Remember I said with that cantilever, it could be a continuous beam, or we could cut two different pieces and glue them together. Well, that welding them up is the gluing them together. And these black triangles indicate that that's what we've done. Let's see if we have any more of those. Oh, look at this. We do have that. This beam here is 2B05 here. It looks like it's 2B05 here, but it's got a cantilever. C-A-N-T, that was cantilever. Let's take a look at 2B05 because it looks like it might be interesting. 2B05. Oh, all right, 2B05 is a W610 by 113. They've given us information about reactions. MC, remember that was moment connect. Moment connect right end, and they've given us a load for how much we have to moment connect it for. MF. Remember that MF means it's a factored load. So we know somebody's already factored this. Cantilever is a W410 by 85. So it looks like where we cross that line, we have two different things we've glued together to pretend that's one continuous beam. And we should be able to see that in this section. All right, both beams can't be continuous here, so one needs to be broken and welded together or moment connected. So see, this 2B11 has a column above here. Well, that should actually be a column below. No, column above. So this beam is continuous from here to here. This beam is cantilevered, but this isn't a column here supporting it. It's got a column above. This beam is moment connected through and supported by this beam. So this beam is doing a lot of work. Let's take a look. We had these joists here, but look at these ones. 2P03. This just looks like it goes from here to here. It looks like it's doing the exact same job as the joists were. So we had our metal deck that exists from here to here, but it's spanning. So these two little lines mean it's spanning from here to here. And these arrows are saying this metal deck exists all the way along here. So if this is my metal deck, this is, I guess this is this end, and this is this end, and this is up here, and this is down here. So it's corrugated in this direction. It looks like 2J01 and 2PO3 are doing the exact same job, interestingly enough. But then like 2BO5, it's got a lot going on. This is a balcony, and see this here? It says our total snow load. So it looks like there's something funny happening here. We don't really know. We don't know anything about snow loads, but that will come up. We'll talk about snow loads in a few weeks. What the heck is this dashed line? Steel bracing, oh, looks like I've got a typo there. Lateral load resisting system. So this is dashed because we're cutting and looking up, but we're cutting through something in elevation. Normally we hatch it, but this is a brace in the wall. Basically what we're saying is we've got this with a brace in two directions. We've got a canopy outline. We've got a low roof here. And we've got our stairwell. So we looked at all the things here. Let's come up to our roof framing plan. So it looks like our roof doesn't come out to here. So our level 2 had a low roof here. And remember, our basement, our interior part of the building was right here on the ground floor. So this is outside. This is a balcony. This was inside below. Up above, our building is pulled back here, and it still has a canopy on our roof. So here are our roof notes. We've got loads, we've got snow loads. It tells us that this is our basic snow load with an ASL, or an accumulated snow load. Again, these are things we're going to talk about later in the term. We've got bracing here, steel bracing here. We've got our section marks, and we've got another beam schedule here. Let's take a look at our third page, which shows us our sections. Now this is great because it gives us a lot of information about our building. So this one right here, you can see that there is our ground floor. So this is cutting through where we had no basement. There's our grid lines, so you can tell what way we're cutting. You can see that we've got our open web steel joists that were here and steel beams over here. So these were our purlins and these are our joists. This is where we have our low roof here, and here's where our high roof is. And this is where the bracing was in our wall. What does this note show? Showing column and pier and footing beyond, but don't normally do this. I wanted to show it to you to show you some context here. So normally I wouldn't show these further away. I'd cut closer to the line to show you something, but I wanted to show you what this typically looks like. So there's the wall we're cutting through, but there's the footing and the pier that support that column beyond. Same here. Look at the roof. You know something looks different from this plane to this plane. This is sloped slightly. Look, you can see it. Over here, we're at the datum line, and over here, we're below it. Roofs get water on them, and they have to slope to a drain. So this is a low point. If we can, and it's easy, we'll slope the structure. If it's difficult and it's hard, we won't. Sometimes we'll do a combination of the two. But if it's straight line elements and a low point is easy to build into the project, of course we'll put the drain there and just let structure do what it can to slope it for free for us. It's a little bit of coordination, it's a little bit of work. We have to know exactly what your roof drain requirements are, but we can put that into the project. Let's look at the next section. So this one looks like it's further down the building. We're still looking at A, B, C, and D. This is where we have our basement. So look at the underside of our footings here and look where they are here. So somewhere on that building, we dropped down our footings. We're cutting through our elevator core. So here's our elevator drops down a little bit. Here is our lateral load resisting system block wall. And we've got structure happening in here. So here is our ground floor. that we talked about. Looks like I am missing a joist here by mistake, so that's just a typo. There should be another joist there. Here are open web steel joists, or a purlin there, a beam. Here are open web steel joists, our purlin, and up at the roof, remember we had that major beam? There's the major beam we'll need. Again, you don't need to know what all of this is right now. It's a long process. At the end of 2 terms, you should be able to create a set of these. But you also need to be able to look at them to be able to learn how to create them. So this is a process. I'm trying to show you what these drawings look like now so you can dig into them, and then that'll help you understand what we're doing as we go through some of this process. And here's our section the other way. So let's take a look at this. This is the one that we were hoping was going to show where we glued 2 beams together. Well, look at this. Here is our non-basement zone. Here's our basement. We come along and we have to drop down. We need this load. If this load was up high, it would try to push in on this wall. So we need to drop it down so we're not hurting this wall. Here's our basement. There's our footing. See, this is where grade is. We're at least 4 feet below grade for all of our footings. We've got our slab on grade, and then we've got our beams and our metal deck. Oh, this is the other one. We wanted to see if our deck was fluted. It's hard to see at this scale, but these decks are fluted cut here. Normally, I would then proceed to have some smaller scale sections. Hopefully for you guys, for next year when you do structures 2, you guys will have this updated with a few more sections cut in it. So we've got open web steel joists here. Here's our major beam that's cantilevering out. This comes along, it breaks here, and here is our balcony that we have. And so look, you can see this beam and this beam aren't the same beam, but remember in plan we showed that they were moment connected together. So we took 2 separate beams and essentially we had to glue steel together. And this is what I always say. If you need glue or something to stick 2 things together in building a model, you need a moment connection. If with this, you can imagine if I glued this joint and this joint together, this wouldn't tip over anymore. What we would have done was made a moment connection. And we're going to look at, and in this term, I do exactly for you guys, we look at the difference in analyzing the internal forces on one of these and the internal forces in one of these. So we will go through and find the internal loads for all of the members in this and all of the members in this. Okay, so that's our steel building. I'll go through the concrete building a little bit faster because a lot of the things are the same. We're just switching some things. And a lot of the information is shown directly in the plan versus schedules, at least for a project of this size. So here's our concrete building. All right, this is our wrong page. Let's go back to the first page. Okay, so here is our concrete building. All of the same information. So it's S100 for concrete plans. We have the same grids. Our dimensions are a little bit different now. Before, we had our grid lines lined up with the center of our steel columns. Here, we have our grid lines to the outsides of the walls. It's a little bit easier for concrete to represent it from the outside of the wall, and for steel, it's very, very handy to talk about it through the center of the steel columns. Same thing here, unexcavated with a basement. Here is our slab on grade, same thing, footing hidden, saw cuts. A lot of the information is the same. Let's take a look at a few things that are different. This blob looks bigger than it did in the other drawing. These are still typically cut looking up. Everything shown dashed that we can't see, hatched if we're cutting through it. Almost everything is the same. The grid lines are in a different location, And these piers look to be a little bit bigger, but that seems to be about it. So see, we have 800 by 800 pier. Everything okay?
Yep.
I'm guessing a child pooped in a diaper. Diaper?
Oh, just for garbage.
Oh, okay. Our 3-year-old is basically a COVID baby. He was 1 when COVID started, and he's been resisting his diaper. So we have 8 months to get him fully potty trained. He's pretty good, but every now and then he likes to surprise us. Okay. So here is our ground floor plan. This, again, looks very similar to our steel project. We've got a lot of the same notes. Some of our loads will be different because this is a concrete building now. Let's look at what's different. Our slab on grade is the same. We already talked about our piers being bigger. Let's take a look at this zone here where we're cutting and looking up at our structure. Before, we had metal deck spanning in this direction with joists every so often. And so we had these little kind of double arrow line going from here to here with structure every so often. What we have now is something spanning from this wall to this wall. And we're saying it is a 300 slab with 15s at 300 top and bottom each way. This should be GS02, not GS01. So I'm finding some flaws in this. Brace typo. GS01 should be GS02. All right, so this is a 300 slab with 15s at 300 bottom each way. What we're saying is, instead of this spanning every so often, we are in the shorter direction taking a bunch of steel rods and spanning them from here to here and encasing them in concrete. So our slab now spans from this wall to this wall. Our metal deck spanned in this direction, but it sat on elements that spanned from this wall to this wall. The other thing that's different in this plan is our stairwell. Remember, in our steel building, we had a concrete foundation, so everything was concrete. But going up, we had a steel building with block walls. Well, this is a concrete building. Why would we stop and make the stairwell block? That would be bonkers. So what we have is a concrete core here. So we have a concrete wall, and that is part of our lateral load resisting system. We'll show that on the next plan as well. So you can see, well, actually on this plan, we still would have been looking up and cutting through the concrete. So we wouldn't have shown anything different yet at this plan, but our stairs were only concrete for one level in the steel building, and then we switched to steel. Here, we're showing concrete on all the plans. So we're gonna have a concrete stairwell. I'm pretty sure I'm consistent with that. Let's see what happens on the next plan. Yes. Okay, so here's the next plan. We have our concrete shear walls. We are cutting, looking up at our second floor. This is our low roof, and this is our balcony. Why would we have this roof low? Well, one of the reasons is if these are flush and water pooled on here, it can run inside your building. You always drop a low roof relative to a floor area. It's absolutely ubiquitous. If you have ever been on a deck, you often have your deck down a little bit. Where that differs is in accessibility areas, but a lot of work is done to avoid kind of moisture flow. And often there is sloping. We'll put a protection above it in some way, anything to protect the system below. Because water getting in things, as you're probably talking a lot about in your building systems lectures, is a huge problem. It's not a structural problem, but it can create a structural problem. So structure will do whatever it can within its scope to prevent that from happening. Okay, exterior slabs are often dropped for build-up for roofing, waterproofing, and keeping rain from doors. Okay. Exterior grids are at the wall lines. There we go. So what is all of this dashed stuff? What's happening? We don't have any of our steel beams cluttering up this area. Let's take a look. This is a 250 two-way slab with 15s at 400 top and bottom each way with 150 drop panels. Drop panels are the thing that we put around columns because we don't like the way slabs act in shear in concrete. Remember I said shear is like taking Jell-O and supporting it on a toothpick. That Jell-O wants to slip down around the column. Imagine if you put a little piece of paper at the top of that toothpick and then sat the Jell-O on it. It would be more likely to hold itself up there. Well, that piece of paper is like our drop panel. We're helping reinforce for shear around our column. All right, what else have we got? We've got these dashed lines. Let's see. Major transfer look at that typo, beams, because they pick up the column above. Oh, it looks like these dashed lines mean that they're a beam. Even though I'm cutting and looking up, I still tend to draw them dashed. Even though we're cutting looking up at these beams, we often draw them dashed, just because it gets too busy to look at otherwise. So looking at the sections of these is going to be really helpful. Let's take a look here. Perimeter beam, show width, then depth. So that's how wide it is and that's how deep it is. So look, all of these beams, they've given us information about the beams. Okay, let's take a look at the next plan. So this is the roof plan. This one doesn't have any beams in this area and just a little bit of beam here to cantilever out. We have our two-way slab, meaning our slab is being supported all the way around its perimeter. Now, what's not apparent in this and would be in a final design is at these perimeters in the slab, we would put a lot of extra steel reinforcing. Basically, we would make beams, but we'd hide it in the depth of the slab so you wouldn't see it stick out below the bottom of the slab. We've got our concrete walls here. They're acting as our lateral load resisting system. We've got our slabs in here, and there's our elevator core. We've got drop panels still. Oh, look at this. We're showing 0 and minus 150. Spot elevations around perimeter and at columns roof will be formed to slope to the drains. So we can do the same thing we did with the steel. This is going to be a low point and a drain will be put there to gather up all the water and funnel it down out to the below the foundation somewhere. Okay, let's look at the third page, which is our sections, because these are really helpful to show what we were talking about with those column capitals and drop panels and everything. So here we are. Here's our section. This is through the part with no basement. There's our foundation walls. Remember, we had we didn't have concrete walls. Here we're showing our concrete column beyond and our pier and our footing. And then here is what we're cutting through. We are cutting through a slab here. We're cutting through our perimeter beams here. So you can see there's a beam and there's a beam. Here's our low roof right here. Here's our beam beyond, that big beam beyond. And here is our drop panel here. And over here at this edge, we actually had a capital as well. So we're cutting through a beam, and beyond we have a drop panel and a capital and a column. Our column got smaller as we went up the building, and here's another drop panel. Here's the same direction but pulled back a little bit where we have a basement. So this is a much simpler drawing. You can see it looks pretty plain. And then here's our section cut in the other direction where we'd be cutting through some of those major beams. We've got our unexcavated area with no basement. Here's our basement. we step down our footings. We're cutting through some major beams here. We've got drop panels beyond. And then here is where we have our balcony, where we drop down. And remember, there was beams that cantilevered out as well. So that is really just a quick look at some drawings. This isn't in the curriculum that I'm supposed to provide to you guys, but I don't know where else you would possibly learn it. It's a hard thing to teach. The best way to kind of get experience with drawings is to use drawings. To have somebody walk through and talk about all the things in a drawing, I get is ridiculously boring, but I don't know a better way to teach it. Having you make drawings is going to be helpful, which we definitely do in the end of structures too. But we have to be able to read them to get to that point. And so we're going to spend a lot of time looking at structural drawings. And some things I'm going to expect you guys to just know. And for a lot of stuff, I'm going to give you just little part plans of structural drawings so that we can do work based on them. Okay, so here are all the drawings. These are just captures of that. But remember, you have these. I gave you the PDFs for these. Okay, so we talked about the typical details. These are the drawings that I created, these are projects I worked on in the past, and the architects have kindly given permission for you to have access to their architectural drawings as well. So Varsity Goldring Center for High Performance Sports is the project I did. In some ways, it's an extremely complicated project, but there are zones of it that are very simplified. MJMA and PatCal both gave permission for me to share kind of a pared down version of the architectural drawings, and I've given you as much of the structural drawings as I can. So what's nice about that is you can look at the same drawing and see what architecture shows and what structure shows. It's also going to be handy when you have questions. Before you come to me and say, how do I draw this thing? If it's a steel project, look at any of these examples I've given you, including this example that I just made, that we just went through. The typical details are important. You'll see how things go together. That's the biggest question I find people have. And I know it. I'm designing a sauna, another sauna. No, I've already designed 2 saunas. I'm doing a bunkie now. But I'm the architect. I am not an architect, but I am trying to do the building science scope of it. And I realize how much I do not know about building science. And so where does the waterproofing go? How do I drain it from my one roof to the other? That's all stuff that usually gets captured on architectural, even though it might not fall in the scope of an architecture's understanding. There are building science people that specialize in this. If you guys know, Bomani and Ted and Alex have all been teaching you courses on this, and if you haven't already, you will be. And I guess Daniel now as well. Daniel's new to the staff this year. So there's a lot of people teaching you that scope of it. I am not great at it. And I'm happy to admit that. And so having everybody work together is how these things get created. So showing the architecture with a structural drawing helps you guys have a reference to go back and look at something. What's interesting about the Cube Lofts project, it's an old project. While I was off with cancer. So 2007, I think, is when I was working on the drawings for this. And we issued the project, and it was a steel building, and it came back twice the budget. It was crazy. What had happened was there was kind of a monopoly on steel because China was preparing for, they say, the Beijing Olympics, but they needed a ton of steel very fast. And so basically there was a steel shortage, and it drove up prices like crazy. And it was a small blip, but the owner freaked out and said, this is ridiculous. Why would you design a steel building? The prices are outrageous. I want a concrete building. So we said, no, we think you should just wait a month or two. Like, the prices are going to come down. But they insisted, so we redesigned it as a concrete building. It took 8 months to redesign it. Some things changed, not a lot, because obviously the architect, it's never too late for a good idea. So the architect, if they had good ideas, implemented the good ideas. And some things had to change just because it was a concrete building now instead. So 8 months later, we issued it as a concrete building, and that's how it got built. By that point, steel had come down, and it would have been cheaper to build the steel building for this particular project. But what's lovely is we have an architectural set of drawings, and then structurally, we have a steel set and a concrete set to be able to compare to each other. So that is a really handy thing to have. Now, these are all old projects, but they're really handy to take a look at. What I would love for you guys to do is just flip through them, look at them on PDF, see if you can figure out what's going on. What is holding up what? Where do things go? If somebody stood in the middle of the slab, where does their load go in the slab? Is it going to that beam? Is it going to that beam? Do a little mental check and see if you understand what's happening before I've taught you too much, because I think intuitively you know, and this is what I'm talking about. If I sit in the middle of this table, if this camera's skewed, but I'm sitting in the middle of this table, how much of my load is going to that side and how much is going to that side? You know that half of my load is going to each side. If I sit down here, how much of my load is going to this side and how much of my load is going to that side? Again, intuitively, I think you know that all of my load is going to this side and none of my load is going to that side. Intuitively, what if I laid full out on the table? How much of my load is going to this side and how much of my load is going to this side? Again, intuitively, you know probably half of my load is going there and half of my load is going there. I know I'm not evenly distributed with my load, but if I was, you understand that half of it goes to each side. So these are the things you intuitively understand that somehow over the next 10 lectures, I'm going to screw you all up and you're going to not remember to think about it basically. So before you ever start any problem with me, stop and think, what do I think is happening? Where do I think these things are going and how do I think they're working? And I tell you, if you do that, you will probably do amazing in this course. All right, I'm going to take a little break and then we're going to talk about tributary area and tributary width. Okay, so let's talk about tributary area. I poured myself a water and already set it down somewhere else. Hold on a second, team. All right, here I am. Okay. The area of load that impacts the design or deflection of a structural element. This is what I was saying. When I sat at the middle of the table, let's do this again, just because I find it very helpful. All right, if I sit right here, way up in the middle of the table, you know that intuitively, half of my load goes to that end and half of my load goes to that end. You know that at that end, at the corners of this table, there are 4 columns supporting this table. You know that this table is spanning to those ends and that a quarter of my load is going to that leg, a quarter of my load is going to that leg, a quarter to that leg, and a quarter to that leg. If I move up here and sit right in the middle of this end, maybe right on the edge, you know that none of my load is going down there and all of it is going to this end. Half is going to this column and half is going to this column. If I switched and put all of my load right here, this is an ab workout to actually sit like this, you know 100% of my load is going to this corner of the table. So you intuitively understand tributary area. Now, what if you took me and turned me into a piece of paper that was evenly distributed across the top of this table? You would know that a quarter of me went to each corner of the table. That is what we're talking about with tributary area and tributary width. All right. I find it very easy to talk about tributaries first as a watershed, simply because getting your head around the fact that, let me use something, Dave bought me a weighted blanket. Here's a good way to talk about it. That weighted blanket, you know, a quarter of its weight is going to each end. What if I put that weighted blanket at that end, and now I sit in the middle? I am different than that weighted blanket. Half of my load goes to that end of the table, half of my load goes to that end of the table, but all of the weight of the blanket goes to that end of the table. So this end of the table is supporting half of Shannon, and this end of the table is supporting half of Shannon and all of the blanket. So the same thing doesn't put the same load in all the places together. Okay, so let's talk about that as a watershed. All right, if you were walking in the river, if you're walking in the forest and you came across a flowing body of water, you'd be like, oh look, a river, how lovely. Now, in the context of anything else, you don't know specifically what that river is called, but you would call it a river. Now, let's say you're walking through the forest and you come to a different body of water. You'd say, oh, look, a river. It's only by knowing the context of the bigger system, if you were drawing it on a map, you might say that one was a creek, because you know that it's smaller than the river that it's flowing into. But to you in the woods, whether it's a creek or a river is almost irrelevant. It is the thing that is a flowing body of water. So as an individual thing, it doesn't really matter, but in the context of the whole, its designation starts to have real meaning. Now, if you're walking through the woods and you come across another body of water, you'd be like, oh, look, a river. But in the context of the overall system, maybe we call that a stream. And a stream just means it's, not quite as, it's not doing quite as much as the creek maybe. But a stream doesn't have to flow into a creek. Our stream could flow directly into the river. There's nothing that says the stream must go into a creek, which must go into a river. Usually it does, but our stream could go directly into the river. Now, you're walking through the woods and you come across a body of water and you say, oh, or a flowing body of water, and you say, oh, look, a river. But in the context of the overall system, maybe we'd say that one was a brook because it was the smallest one of them all, or it had the least flow. We don't really know what the designation is, except that in the context of the whole, the brook is the one doing less work than the stream, which is doing less work than the creek, which is doing less work than the river. Often, a brook could flow directly into a river or a creek, but often they run into a stream. So there's no specific order they have to go in, but usually it is brook, stream, creek, river. So again, context is everything that makes it important. Now, in a watershed, it could snow over here and rain over here. This snowfall does not necessarily happen over the entirety of this system. This brook could see 100% snow over its tributary. This brook could see 100% of this rainfall over its tributary. This creek would see all of the snow from this brook's tributary, but none of the rain from this brook's tributary. But this river would see 100% of the rain from this brook's tributary and 100% of the snow from this brook's tributary. It is very similar to this column taking 100% of the weighted blanket load and 50% of my load. It didn't necessarily take all of both loads. Now, if this is the tributary of a brook, this would be the tributary of the stream, that would be the tributary of our creek, and that is the tributary over the river. But only this portion is seeing snow and this portion is seeing rain. So even though the river has a gigantic tributary, not all of that tributary is seeing all the loads simultaneously. And this is very similar to how our buildings work. If, for example, we wanted to say we came across a piece of steel in a project. Now the columns are going to be slightly different because you would probably obviously figure out a column is a column. But if you came across a piece of steel, anything standing upright, you'd probably designate a column. But if you came across a piece of steel in the floor system, you'd say, oh, look, that's a beam. But you wouldn't know if that beam was something we called a girder. And maybe you come across a piece of steel and say, oh, look, a beam. Or maybe you come across a different piece of steel and say, oh, look, a beam. Purlins, beams, and girders are all beams. They are all doing the same job, which is spanning from one distance to another, picking up a tributary. But purlins are often doing a very light amount of work. Beams are doing kind of a regular, normal amount of work. Girders are usually doing something extra, something beyond. Usually, a purlin spans to a beam, and a beam spans to a girder, and a girder spans to a column. But not necessarily. Often our beam will span directly to a column. Sometimes our purlin spans directly to a column. So looking at the context is really important. I have a crying child running towards me. So if this is our 5th floor live, and this is our 4th floor live, what's wrong, guys? Come here. What happened?
I accidentally kicked Duncan off of the couch.
Then you fell and hit his head on the floor.
Okay.
Not this
All right.
couch.
Duncan, will you sit here on my lap for a few minutes and snuggle? Okay, guys, I'm recording a lecture right now. You want to say hi to everyone? Why is there a tree on it?
Yeah.
Well, that's a good question. This is a tributary. I am saying that if it rained over here, this little bit would pick up rain and it would flow all the way down to here. And if this little bit had snow, all of the snow would flow down here to here. And it's very similar to a building. If we had somebody standing over here, this purlin would pick up their weight and it would go to a beam, which would go possibly to a girder, or maybe it would go directly to a column. If somebody stood over here on the 4th floor, it would go to this purlin, or maybe it would go directly to a beam, or maybe that purlin would go to a beam. And eventually, it would all get down here to our column. You sit on my lap while I talk for a few minutes? Okay, come here. So I apologize, guys. This is what it's like with kids in COVID. All right? All right. So let's take a look at that same thing as a building system. Okay?
Yeah, but I want it to be a different tree.
You want it to be a different tree?
Yeah.
Well, let's take a look at this and see what it looks like. All right. Like I said, if you came across a piece of steel in a building, the column's pretty easy to tell. It's the thing that's standing straight up. If you were walking through the building and you came across a piece of steel, you would definitely say that's a beam. But maybe in context, you'd change your mind and say it was a girder. I'm going to give you later in the term all of the information to be able to differentiate between these. If you came across a piece of steel in the building, you would say, oh, look, that's a beam. But in context, maybe you'd be able to say, yes, that one is actually a beam versus a girder. And then if you're walking through the building and you see another piece of steel, maybe you'd say, oh, look, that's a beam. But in context, you'd be able to say, oh no, that's a purlin because it spans to a beam. There's a lot of them and they're not doing that much work. I'm going to say that that one's a purlin. Whereas this one is picking up purlins, probably makes it a beam. And this girder, it's just a beam, but it's a beam picking up beams. It's doing an extra level of work. And so we'd call that one a girder. We're going to talk about this more when we talk about size and guidelines. We're going to talk about purlins and beams and girders a lot when we talk about size and guidelines. And so here you can have load. Maybe it's not sitting directly on this girder, but because these purlins are picking up load and it spans to this beam, this girder has tributary on it. Okay, what is a tributary width though? Remember when I had this element here that was representing our deck and it spanned from here to here? I am saying the tributary width is half of this piece of paper. So it is loading all along that beam equally. So if we break down area over every meter...
It doesn't look like a...
Do you want to go back in the other room while I finish up
It
here?
doesn't look like a duck.
Okay, let me finish this slide.
Come on, Donkey.
Oh, okay, Duncan, I'll come in just a second. I just want to finish this slide and then you can join your meeting. So tributary width is if we break down every meter along the element's length. So what I'm saying is, Duncan unfolded my corrugated paper. Okay, so we've got this length and it has some amount that's sitting on a beam. So this beam right here, every bit of its length is picking up some amount of the deck, which we know is half of it. So that's the tributary width. The full area of this beam is half of this deck and the full length of the beam. But what if we just said, we're saying that there's a little bit of load acting on this beam all along its length. That is the tributary width of the beam. Basically, it's one component of its tributary area because sometimes it's easier to break that component out. Think of it this way. When I sat in the middle of this table, you understood that a portion of my load went to each one of those legs. But if it was this type of table and I sat in the middle here or I laid across this way, you know half of my load is coming over here, but it is half of this tributary width of the table and it's all acting equally along this beam here. Yeah, eventually a quarter of it's getting to each of these columns. But for this beam, its tributary width is half of the table. And so some amount of that load is acting along every tiny little bit of that beam. And that is tributary width. Okay, let's start looking at some examples. And this might show up for you guys. It might be a different kind of scene in the background because Dave now is in the middle of a meeting and I've got to take over kid duty. Okay, so it is now late in the evening and my kids are in a bath. So we'll finish up our tributary area and tributary width conversation. So what I'm going to do is I have this plan and I'm going to go through it as an example. I'm going to talk you through it. And then later in the slides, there is another example that you guys can go through with worked out solutions, kind of as an extra set of worked out problems to prepare you for the assignment. Take your time in the assignment, talk to each other. They get progressively harder, or maybe not progressively harder, but there is one hard one, and it's the very last one. And we're gonna have to start to get good at this. This is gonna have to be the easy part. Now, I will say, kind of the problems that go with it get easier, and I'll start to give you easy layouts, very similar to this. So this is an easy layout. The next one is a little bit harder, and your assignment is very similar to it. But I want to give you the hardest stuff now, early in the term, for doing tributary area and tributary width, so that when we need to be able to do it like second nature later in the term, you're able to. Okay, so let's take a look at this plan. We've got grid line A, B, C, and D, and grid line 1, 2, and 3. These are all 6 meters apart, and these two are 8 meters apart. So 3 bays at 6 meters each, and 2 bays at 8 meters each. So that means this distance is 8 meters, and this distance is 6 meters. Now, let's start talking about elements one at a time. Let's talk about RJ01. So let's talk about this joist right here. We want to talk about its tributary width. So what's not apparent here, because it's not really drawn, is that there's going to be deck of some sort spanning across here, similar to our corrugated piece of paper, is going to be sitting on top of all of this roof, and there is something supporting it every so often. This joist is one of those things. So we have a series of joists underneath here, and we want to know what the tributary width of this joist is. Now, it's one piece of deck. How much of this distance here do you think goes to this joist? If you said intuitively half of it goes to this joist, you'd be right. On this side, intuitively, how much goes to this joist? Again, it's very similar to our table problem, half of it. So let's see. So if this is 6 meters, 2, 4, 6. So each one of these spaces is 2 meters. So if we said half of this would be supported on this joist, that's 1 meter, and half of this distance goes to this joist, that's 1 meter, the tributary width of this joist is 2 meters. Let's draw that as an illustration. So its length is 8 meters. Its tributary width is this tributary width, or 2 meters. So its length is 8 meters. Its tributary width is 2 meters. What's its tributary area? Or what area of this roof does it support? What area of all of this is supported by this little joist? Well, I think most of you intuitively would understand that it's going to be a triangle like this. Or the length times the tributary width. Or 8 meters times our 2 meters. So 16 meters squared of tributary area on this joist. What's going to be really helpful later in the term when we start talking about beams and joists is going to be talking about tributary width. That's going to be something that we really like to use, but I also find it helpful to talk about tributary area. So understanding that this is the tributary width and that's the length, and then the whole area it supports is its length times its tributary width, is going to be a handy tool to get our heads around. Well, look at this. It looks like we have all kinds of elements that look absolutely identical to it. So every single one of these has a tributary width of 2 meters and a length of 8 meters. They are all identical. Well, what about we call all of them RJ01? Which is exactly what you saw in those drawings that I showed you earlier. That everything that was an identical length with supporting the identical tributary width all had the same name. So all of these would be RJ01. Let's take a look at another element. I don't know what one's next. Okay, RB01. So let's pretend this is our table, and these are our columns here. And this is like the table that had the beams at the end of it. And if I put all of my weight right here in the middle of this bay, how much of it goes to this side? I think intuitively you understand that half of it. This is just like our table. Well, what we're really saying is half of this entire distance gets supported by RBO1. Or if this is 8 meters, half of that 8 meters goes to this beam here. How long is RBO1? Well, this is 3 bays of 6 meters. Its length is 6 meters. So RBO1, a length of 6 meters, a tributary width of 8 meters divided by 2, or 4 meters. So its tributary area is 6 times 4, or 24 meters squared. Do you see any other beams that look identical to it? I see a few. All of those. So look at this. We just took 1, 2, 3, 4, 5, 6, 7, 8, 16, 17, 18, 19, 20, 21, 22. We took 22 elements and we only have to design 2. So recognizing these patterns can actually save us a bunch of time as well. All right, let's look at our next element. Let's look at RBO2. So RBO2, it looks like we've pushed 2 tables together or supported 2 tables on one set of columns here. So let's imagine this was one of our tables and this was one of our tables. If you break it into one at a time, it becomes really obvious that half of this table goes to this beam and half of this table goes to this beam. Or if this is 8 meters, 4 meters of it goes to RBO2. And if this is 8 meters, 4 meters of it goes to RBO2. Or 4 meters plus 4 meters. 8 meters. How long is RBO2? Exact same as RBO1, it's 6 meters long. So we've got a length of 6 meters, a tributary width of 8 divided by 2 plus 8 divided by 2, or 8 meters. So that means our tributary area is 6 times 8, or 48 meters squared. Do we have any other beams that look the same? Yeah, we've got 2 more. These ones look identical to it. So now we're getting pretty close to the end of designing our beams. We're doing a pretty good job. Let's take a look at a column load. I don't remember exactly what I did here, but we're going to say that this roof is supporting 3 kPa. Don't worry about what it is, but imagine what we're saying is there's some loads spread evenly all over this roof. So every little bit of this roof is something that is 3 kPa in weight, or every kilonewton per meter squared has every meter squared has 3 kilonewtons on it. We're going to talk about that later in the term. I don't remember adding this part into this. So maybe I have even taken it out. Let's take a look. Let's talk about column 1 here. All right. So column 1, now we're really talking about this table idea where if this is our table, we know that half of this and half of this goes to this column, or a quarter of this total area goes to column 1. Or our 8 meters divided by 2 times our 6 meters divided by 2, which gives us 3 times 4, or 12 meters squared. Don't worry about this part of it. We're going to come back to that later in the term. We're going to figure out what that means. We're going to talk about this, but this is handy. When we start talking about loads, come back to this slide. It's going to be handy for you. But what we're really saying is that for every meter squared, we have 3 kilonewtons. And if we have 12 meters squared, the entirety of load on that column is 3 times 12, or 36 kilonewtons. Do you guys see any other columns that look identical to this? Yeah, those 4. They are all picking up 1/4 of a bay. Let's look at column 2. Well, column 2 looks like it's doing the exact same thing as column 1 in this bay, and then the exact same thing as column 1 in this bay. where we've got our same 8 meters divided by 2, so 4 meters. But then here, each of these bays is 6 meters. It's picking up a quarter of this bay, so we've got our 6 meters divided by 2 is 3 meters. But the same thing happens in this bay. This is where it's handy to draw it. And this is what I would always recommend if you're unsure. Take a piece of paper, draw it, color it, help yourself identify it. That's why I've broken these into different colors. Let's take a look at this. What we're really saying is 6 meters divided by 2 plus 6 meters divided by 2 times our 8 meters divided by 2. Intuitively, you understand that this is how much of the area this column is supporting. Doing the math tends to freak you out, but if you take it and draw it first, it starts to be a very handy way to talk about it. So we have 6 divided by 2 plus 6 divided by 2 is 6 meters here, and 8 divided by 2, or 4 meters for this length. Our total tributary area is our 6 meters times our 4 meters, or 24 meters squared. Do you see any other columns that look just like that? Yeah, C1, B3, and C3. All of those look identical. Let's see what else we've got. Column 3. All right. This one is now picking up a quarter of this bay and a quarter of this bay. If that's 8 meters and that's 8 meters, that distance here is 8 meters. And then it's going to be picking up 3 meters in this direction too. Or 6 divided by 2 is 3. 8 divided by 2 plus 8 divided by 2 is 8. Our entire tributary area for column 3 is 3 meters times 8 meters, or 24 meters squared.
I'm going out to light the sauna. You can keep the kids from drowning it and do a lecture at the same time, right?
We're lighting the sauna.
Yeah.
Yes. Yes. That's awesome. Thank you. You know how, right?
No.
Sauna is my design, so. We had an 8x20 like trailer, like the big enclosed ones, and we built inside of it an 8x8 sauna, essentially. So we built partition walls, we insulated it all. I bought a sauna fireplace online, and it's a wood stove fireplace, and on a cold day we can get it up to 200 degrees Fahrenheit inside that sauna. So it's pretty nice. Okay, do we see another column that looks like this one? Yeah, this one over here. What's interesting is this area is the same as this area. It's proportioned a little bit differently, and maybe you'd want to make them the same, call them all the same column type. It's harder to kind of identify them differently. I would probably keep them as 2 different labels, but again, no big deal. It depends on what mood you're in at the time. So now we've got those 2 that are the same. All right, let's look at column C4. This column is picking up a quarter of this bay, a quarter of this bay, a quarter of this bay, and a quarter of this bay. So we know it's picking up 4 of these. And if you wanted to think about it this way, C2 was picking up twice as much as C1. C3 was picking up twice as much as C1. And C4 is picking up 4 times as much as C1. Because really, it's 4 of these little squares. So there we are. We've got 6, here, let's make me a little bit smaller. We've got 6 divided by 2 plus 6 divided by 2 times 8 divided by 2 plus 8 divided by 2, or 6 times 8 is 48 meters squared. Again, if we wanted to say that every square meter of this surface was supporting 3 kilonewtons, we would say that we've got 144 kilonewtons on this column. But don't worry about the last line calculation too much. That's just to kind of help give you some information for where we're going on this. Well, what happens if we have weird layouts? Look at these beams on a diagonal. Well, this beam here, if you wanted to look at it this way, at this point here it's picking up half of this joist. At this point here it's picking up half of this joist. At this point here it's picking up half of this joist. So really, it's just following the half line point of all the beams it's supporting. Same on this side. What's interesting is if we drew this out, all three of these beams are actually supporting the same tributary area. That is not apparent unless you did the math or drew it out. Now, this beam here is actually the same as this beam. These two beams are the same, and these two beams are the same. And this is where it's really handy to sometimes draw these things out. Okay, there's one more plan with a set of examples. Now this one is written in imperial. So we've written it in feet and inches, and you're gonna have to convert it into metric. It's worked out on the next page. Take a few minutes and I want you to solve L2J01. And what we're saying is we have a joist that spans from this wall to this beam, and it exists every 16 inches. If you wanted to, we could say, I wonder if it'll let me do it easily, that every 16 inches we've got one of those joists. And what we're saying is that is 16 inches. All right, so we want to solve for L2J01, L2B01, so this beam, L2B02, this beam. Now these are at 16 inches on center as well, and L2B06. I'm not going to go through these right now. I have the solution worked out on the next page. So take your time, work these out. These are practice problems with worked out solutions. These are going to be similar to the assignment question. So just take your time and try to figure these out and see how it works out for you. You've got some extra time in this lecture time slot. Okay, here is the first bit of information for the project. It's broken up into two parts, part 1 and part 2. You guys can read through this, but here's what I wanted to stress for you. Part 1, you should start thinking about now. The key to this is you're going to have to pick a static object. Static means that it's standing still, or it is stationary, it isn't moving. A bicycle is not a stationary object. A bicycle leaning against the wall is a stationary object. This is where so what we're not doing is trying to design a building. We're not trying to design anything, but what we're going to do is draw some free body diagrams and talk about our objects. But we don't need them to be buildings. What I want you to do is think about an everyday object around you. I have seen people be as boring and bland as can be, and I've seen people really excel and do extraordinary cool things. What you are going to be doing is picking an everyday object around you that is not a building, and you're going to think about the worst case loads your object can see. Not, let's say it was a table. Well, I don't care about a cup sitting on the table. That's not the worst case load that's going to be on a table. We want to talk about the worst case load. That's reasonable. We're not going to stack gold bricks on a table either. That is outside the realm of normal. What is reasonable for that table? Well, maybe me sitting on it. Maybe a stack of books on it. something in there. This is where you have control to think about what is a reasonable thing somebody designing this table would do to it. I've seen people do things like a teacup. So they've thought about a teacup sitting in a saucer filled with liquid, being held by somebody in the hand, because it's a different system when it's being picked up and held. I've seen very boring things, like somebody doing a table. Please don't do a table. It's about as boring as you could possibly imagine. I am going to, several times throughout the term, basically draw the free body diagram of a table, which means it's hard for me to give you lots of really exciting points within it. I have the point system. I've kind of talked about what's going to happen in this project. So take the time. This is posted. You can read the project outline. And part 2 will start to be more apparent as we get through the term. But feel free to reach out with any questions. You want to just start thinking about your object now. I gave some suggested dates for where you should be in your part 1 project. You can do it with a partner or not. It's up to you. Okay, so today's takeaway tips. You should know how to read a set of structural drawings. So take the time, go look at those drawings that I've posted for you. You don't have to print them off, but you should take a look at them and see if you understand what's happening. Put yourself as a person on various objects within it and imagine where your load goes. Where does that transfer through the building in your mind? And for studying tips, you should be able to produce structural drawings. Now, obviously, that is a bit far-fetched. You're going to get better at that. I don't expect you to be able to do that at the end of this term, at the end of this class, let alone at the end of this term. Part of it's going to come with what happens next term as well. But you should be able to calculate the tributary width and the tributary width loading a beam and tributary area loading a column. So that should also say tributary area loading a column. And so that will be in it for you when you look at this. So that's everything that I needed to get through for this week. Next week, we're going to start getting more in depth with things. So hopefully my kids are not home by next week. We'll see. Thank you very much for your patience this week, everyone.